So, can everybody see my Chrome?
Yep. Thanks, Edwin.
Yep. Looks good.
Yep. I think, I'll just echo what Matt said, and I do think Discord is really good in terms of rooms and streaming, but obviously not everybody can. There is a barrier to entry, as you just seen now. So let's just quickly go through this question. I won't take more than 10 minutes on this. So this is a very famous dynamic programming question. So I've been getting requests to do more recursion practice and especially more dynamic programming. And dynamic programming is essentially just a fancy way of saying recursion. So basically, we're just having fun with recursion for tonight. So this question is asking, given two words, word one and word two, essentially two arguments, find the minimum number of operations required to convert word one to word two. So we have three operations permitted on a word. We can insert a character, delete a character, or replace a character. So this is a famous distance known as a Levenshtein distance that allows us to convert one word to another word by just performing these three operations. So it's very intuitive, and our task right now is to implement the Levenshtein distance, which is a subset of edit distance. Between two words, and it's used a lot in terms of comparing string similarity between two words. So it's very relevant, and also it's a good way for us to practice recursion. So let's start with this first example. Given word one, horse, where you need to convert it to ROS, to the word ROS using the minimum number of operations, and we can only use it to insert character, delete a character, or replace a character. So in this explanation, just so we're very clear, so in order to convert word one, horse, to ROS, this is the minimum number of operations. It's 3, and it's essentially we first replace H with R. Then when we have this new word ROS, we remove R in the middle, and then once we remove R in the middle, we have the word rose, and then we remove the character E at the end, and then we get the ROS of what we're essentially finding. So what you should be thinking in your head right now is essentially a brute force solution, and the brute force solution would thinking to ourselves is, how do we essentially try each of the combinations of inserting a character, delete a character, and replace a character at every single point of the word horse, right? And then if we think about it some more, a more elegant solution would be essentially, how do we actually compare the word one and the word we want to convert it to, word two, in such a way that we can modify and try to keep the number of operations as few as possible from word one and word two. So instead of just looking at word one, we also want to leverage as much as possible word two. So thinking about essentially how do we keep the minimum number, and also how do we essentially traverse word one and try each of the combinations, it lends itself very well to a recursive solution. So when it comes to making a recursive solution, I always like making a helper function. It's definitely not necessary, but I think it helps a lot in terms of just calling a recursive function inside the regular function that we're given, the min distance. And we're going to start with essentially index pointers. So index pointers would essentially be a lot faster than if we were to slice the word. If you're familiar with Python, slicing the word essentially would be the slice notation with the colon. You'd be doing the word one and doing that colon where you start at 0.0 and then you slice all the way to the end. But I just really want to start with index pointers because that's essentially how we think about this. Is we're really starting with what is the exact index of each of the words and how do we compare the two together. And I'm going to actually start with 0 and 0. So both word 1 and word 2 each respectively starts at index position 0. And then let's actually define the helper function here. And we could say word 1 index here, and then word 2, it will be argument word index. And now that we have essentially both our indexes, and when we're calling this helper function, we're starting at index 0. When it comes to a recursive solution, we always want to start with the base case. So we start with x essentially X would be word1 underscore index, and Y would be word2 underscore index. So I'll refer to them as X and Y. But when we come to spell it out, you always want to make it as clean as possible to the exact programmer. But when it comes to, for example, the first word's index or X, we want to make sure that in the base case, it should be straightforward to know at what point we should end. And of course, we should end when the index is either greater than or equal to the length of the word 1. Right? And then once we reach that stopping point, what happens if we still have stuff remaining in the second word? Because it's certainly possible that when we've actually finished our traversal of the first word, we would still have a remainder of the second word that's still present. So then we have to, and then that would be the number of operations needed to finish up the rest of the second word. So as a base case, what we should do is we actually should return the second word, well, the length of the second word, and we should subtract the word2 index, because if we've moved the index of the word2, or we've moved the pointer of word2 to further to the right, then we should also just take the remainder of word2 index and the length of word2, and that will give us a remnant of what is currently the remaining part of word2. So by similarity, let's also do the same for, to finish up the base case, let's also do the same thing. Is if our word2 index is greater than the length of word2, we should also have similar logic where we return the length of the remaining word1 minus word1's remaining index. So that would be our base case. And that would help us track and execute the recursion. So now here comes the really fun part, is what do we do when let's say horse is very similar to horses, and then when we essentially go through the first word and we're comparing it with the second word, and essentially they're the same at the same index position. So then what we could do is we can actually skip and increment both the indices and push them one further to the right. Remember, we're starting at the 0th index for both the word. So we're starting at the very left at the letter H for horse, and when we're traversing word 1, we're just moving the index position from 0 to 1 to 2 to 3 to 4. And if they share the same exact letter and character as the second word, then we should just increment, we should push out both indices of both of the words. So if word 1, at word 1 index is equal to word 2 index, we should essentially continue the recursion, but let's increment the word 1 index by 1 and the word 2 index, or y, by 1. So that's if they share the same exact character and the same exact index position. Now the fun part is where do we actually perform the insert, the delete, and replace operations and compare each one of them together? And how do we try out each of the combinations in play? So essentially what we have to do is we have to think about what the differences are for each of these operations when we do a recursion. And when we think of recursion, I always like thinking of what we want to return, and then what do we want, trusting that the remaining rest of the recursive function is going to return what we want. At each step, what do we want to happen at each recursive step until it hits the base case? So obviously, because every time we insert, delete, or replace a character, we have to increase the number of our whole task is to find the number of operations required to convert word 1 to word 2, right? So every time we do an insert or a delete or replace a character, we have to essentially penalize ourselves by incrementing the minimum number of operations required by 1. And how do we essentially, when we perform the recursion, and we essentially traverse through the remaining and try out all the combinations of word 1, how do we change the indices? So when we insert a word, we're not exactly penalizing the first word. we don't have to increase the index. We don't have to move the index pointer of where the current word is. But what we do have to do is, because we're inserting a character, in order to, for example, you can see in this example in execution, we're adding the letter U here to make execution equal to execution. We're inserting the character U, so we have to. It's going to be essentially a flip of insert. So word2 index here. Now for the fun part, replace. Remember, each of the insert, delete, and replace calls is +1. It essentially takes one additional step of operations that we have to return. But in terms of when we do the recursive step, what we have to do is we also have to increase each of the indices by 1. So we're moving the index pointers by 1 step to the right, so that we're looking at the next additional index character for both word 1 and word 2. So that essentially resolves the recursion. And because we want to find the minimum number of operations, we just don't want to run this recursion willy-nilly in terms of it returning all possible combinations or one possible combination. We just care about the minimum number of operations. So what we need to do is we need to return the minimum of these insert, delete, and replace recursive step. So let's try running the code. So we have a mistake here. So you can see that in our replace is exactly the same as delete. So we actually have to increase this by 1. And then let's run this code, because the replace, essentially, we have to move both index pointers for both the word 1 and word 2. You can see that this is accepted. Let's run it again. Let's submit it, and let's see if this works. And this will fail because LeetCode has a time limit exceeded. So even though this solution is valid, they really want your solutions to be very optimized, because recursion also is very demanding on the call stack. And this solution is not optimized at all. It's a very naive recursive solution. So what we need to do is, as Matt was talking about last week, we use memoize decorators in order to try to make sure that that it doesn't repeat a lot of the recursive steps as we try each of the combinations of insert, delete, and replace. So in practice, I think most people will use this LRU cache, and I'm going to set the max size to be none, and this should work. Let me try. Let me get rid of that. All right. So let's submit this, and essentially this helps shortcut a lot of the memoize. I don't want to write because we're short on time in terms of like passing in a memo argument here and then checking to see if it exists. So a memo is just a fancy dictionary where you store pre-computed results. So I don't want to write that all down, so I just use the LRU cache and set the max size equals 0, max size equals none. So every time we call the helper with the same index pointers, it's going to use the pre-computed cache result instead of trying to recompute it again and again. And you can see that this is faster than 95% of most Python solutions, and that's because we're not using slice. We're using the LRU cache, and because we're using these index pointers, everything's going to be a lot faster, and also in terms of memory, it's going to be very optimized. But yeah, I think I took 15 minutes. So that's it for me. If you have any questions, let me know.
Awesome. Thank you, Edwin. As always, very great to hear from you, and thank you for taking the time to present on that.
Yep.